we are evaluating these things. They are definite integrals, so we know how to do that. Integrating from 2 to x, 2x. And so to start off this thing, we're going to find the antiderivative. Harrison, what's the antiderivative of 2x going to get me?
X squared.
X squared. He increased the exponent by 1, and then divide by the new exponent. So it became x squared, divide by the new exponent. Hey, cool. F of x is x squared. Okay, we found the antiderivative. Okay, once we have found the antiderivative, then we're going to evaluate that guy, starting at the lower bound, going to the upper bound. And so the fundamental theorem of calculus, that is what we've learned so far. That would be capital F of x minus capital F of the lower bound. Okay, so we plug in x. We take x, we plug it in for the x in the x squared, so that's just x squared. We're plugging in, okay? We're taking that x and putting it in place of that x, so it's still an x. Minus f of 2, okay? So we're going to take 2, we plug it in, x squared minus 4. That is the definite integral starting at 2 and going to x. Everybody okay with what we just did there? We just did the integral. We did the antiderivative. What if, after you finished that problem, I gave you this direction? I said, now take that number, or take that value, and do d over dx. What would you be doing if you found d over dx? Take the derivative. So we took the antiderivative, we did the integral there, and then once we get done with that, now let's take that final answer, and we're going to do d over dx. It would just get me 2x. Look what I started with. Look what I ended with. I just took the antiderivative and then the derivative. Guess what happens when you do the antiderivative and then you take the derivative of it? They cancel out. They're the original. The 2 and the x are the key here. Okay? The antiderivative, the derivative, you're just in a cycle. You're going back and forth between the two. That makes some sense to you. Okay? Especially when x is in the top upper bound and it's just x. That's the key for what we're doing today. Make sense on this first one? That one's pretty straightforward. The second one makes a little less sense. Let's look at it anyways, though. Okay, you can do this the long way. Okay, doing this the long way isn't that tough. So we're going to start off. We're going to find capital F of x. Guess what? It's the same. This time we're going to evaluate this guy starting at x squared and going to 2. So what's different about this one? X is squared. That's important. Where else is the x squared? On the bottom. It's in the denominator, or not in the denominator. It's the lower bound. Those two things are what's going to change this problem. Okay? So we're going to evaluate this thing. So we're going to find capital F of 2 minus capital F of x squared. Capital F of 2 is still 2 squared. That gets you 4. F of x squared. So now we're plugging that in here. So it's going to be x squared. Sorry. Let me try that again. X squared squared. And I'm subtracting that. So I'm going to subtract x to the 4th. That is what this definite integral is. From x squared to 2 of 2x dx, it's this guy, 4 minus x to the 4th. Again, today the whole idea is taking the derivative of that. So what if on the outside I said take the derivative of that guy? What's the derivative of 4 going to get me? Nothing. The derivative of x to the 4th is going to get me negative, multiply by my exponent, subtract 1 from my exponent, negative 4x cubed. It seems like we just changed two things. We flipped the bounds, and we made it x squared instead of an x, yet our answer all of a sudden is significantly different. Everybody see what's happening there? This one's easy if it's the first one. If it's just x with an upper bound of x, it's whatever you started with when we take the derivative of the antiderivative. It's just straightforward. They go back and forth. The second one, two things are happening. The first thing that's happening is the x is in the bottom. We don't want the x in the lower bound. We want x as the upper bound. How could I make x become my upper bound? Make it negative. A reminder that if we flipped the bounds, if I made this the x squared up there and the 2 down there, we can just make that whole thing negative. That is where this negative is coming from. Okay? If I would have just plugged in x squared, I would get this problem. I would get 2x squared, and there'd be a negative in front. But the problem is I want it to be 4x cubed. What's the derivative of x squared? 2x. And so we take this answer and we multiply it by the derivative of whatever we plugged in. If it's just x, we didn't have to do anything because just x is 1. But what's the derivative of x squared? 2x. That is where I'm getting this negative 4x cubed from. The x has to be in the upper bound. Okay? And if it's more than just x, we got to multiply by the derivative. That is the main, most complicated thing we're learning today. Questions so far? No. So we've learned the fundamental theorem of calculus. Technically, what we have learned so far is the fundamental theorem of calculus part 2. Again, that was just definite integrals. Okay? Upper bound minus lower bound. That was the fundamental theorem of calculus. Here's what the fundamental theorem of calculus says, part 1. It says if f is continuous on that function, okay, where the function, capital F of x, is equal to the integral of f. Okay, so it's the antiderivative, basically. If that's true, then there's a derivative at every point of x, and the derivative of the integral cancels each other out. See how that works? The derivative and the integral. Those two things next to each other get you back to what you started with. You started with f of t, it made it f of x. It's the same difference. Okay? They're the same problem. It's just whatever your upper bound is, you can plug it in. That's the fundamental theorem of calculus. Basically saying that the two things work in tandem. Okay? That one is the opposite of the other. Okay? Let's look at this first one. It says h of x is equal to negative x minus 5. Lowercase h of x, we're going to call that the derivative of h prime. Okay? So capital H is that, h prime, which is lowercase, are the same. Let's evaluate this guy starting at 6 and going to, or starting at negative 3 and going to 6 of h of x. It seems kind of strange. Let's do it. How would I start off with this problem? What would I want to do with h of x if I'm doing a definite integral? Antiderivative. What is the antiderivative of h going to get me? Capital Hx. We're going to get capital Hx. When I do the antiderivative, it gets me that. And then I'm going to evaluate capital H of x starting at negative 3 and going to 6. That is just the antiderivative. We didn't do anything fancy there. Okay? Oh, h is the derivative, so the antiderivative is negative x minus 5. Cool. We're going to evaluate that thing. So we're going to find h of 6 minus h of negative 3. They told me exactly what that equation is. It's right here. Plug in, get an answer. Work with your neighbor and find one. Does that projector sound louder today than normal? It sounds like it's going to explode. Don't explode on me, projector. Show me with your fingers. What are we getting? A little bit better than this one. The two numbers that I've gotten all day are negative 9 and negative 13. Let's see which one is better. So negative 9 or negative 13. So when we look at this guy, we're doing h of 6. Negative 6 minus 5, that gets you negative 11. Over here, it's minus all of this thing, negative 3 minus 5. Negative 3 is a positive 3 minus 5 is negative 2. But I'm minusing that negative 2. It's negative 11 plus 2. It's negative 9. Make sense on the first one? Try the next one. Find the integral from 3 to 12 of g of x. We did g of x. We evaluated that thing starting at 12 going to 3. So to do that, we just did capital G of 12 minus capital G of 3. You plug in 12 and 3, you get square root of 36 minus square root of 9. 6 minus 3, it gets me 3. That's pretty straightforward, but what we just did there is we are taking the derivative of the integral. Okay? We said that the derivative was this and then worked from that direction. Pretty straightforward. Okay? Let's look at example 1. We are finding d of dx. We are finding the derivative of this integral right here. This is exactly what we did in Belwork. We are going to do it the long way one more time, and then we're going to learn the shortcut. Okay? So the long way. Let's do what's in green first. We are doing the integral of that thing. And so if I want to find the integral of that, I'm going to find capital F of t of that function. So my function is t squared. Jared, what's the antiderivative of t squared going to be? Yep, I'm going to increase my exponent, so my new exponent is going to be 3. Yep, and then 1/3. Yep, right idea there. He's increasing the exponent by 1 divided by his new exponent, so it's 1/3 t cubed. Cool, we found that. Then we go upper bound minus lower bound. We're evaluating that thing, starting at negative pi and going to x. So it's 1/3. Sorry, let me actually write out what I'm doing here. Let's try this again. I'm finding capital F of x minus capital F of negative pi. And so I'm plugging in x into that equation. It's 1/3 x cubed minus 1/3 negative pi cubed. Just like that. That right there, that is the definite integral of that function. Any questions to that point? That is not what it asked me to do. I found the definite integral. I found what was in green, but then it also said, cool, once you've done that, you are taking the derivative of that guy. So I want to take the derivative of that whole thing. So we've got two parts here, the 1/3 x cubed and then 1/3 negative pi cubed. 1/3 x cubed, I'm taking the derivative. So remember how to take derivatives. You multiply by the exponent and you subtract 1 from my exponent. What is the derivative of 1/3 x cubed going to get me? It is x squared. We multiply by the 3 and we subtract 1 from my exponent. That is x squared. What about the derivative of this thing? This thing looks really ugly. Negative 1/3 negative pi cubed. It is nothing. Nolan, how do you know it was nothing? That's a value. Great answer. That is just a number over here. This is a constant. As ugly as it looks, it's got pi in it. I don't care that pi's in it. Pi is a number, 3.14. I'm cubing it, cool. I'm multiplying it by 1/3, cool. It's still a number. And when you take the derivative of a number, it goes away. Notice what our answer was in comparison to what I started with. I took the derivative of the integral. Did it matter? Both things are canceling each other out. Basically, all we had to do was make the t the letter x, and we're done. Okay? We substitute in that x, and we're done with that thing, and that's our answer. So look at example 3 down below. Again, we got to check two things. We're starting with a number. We're going to x. X is our upper bound. We're taking the derivative of that integral. Because x is in my upper bound and it's just x, all we have to do with this guy is plug x in. My answer to this question, what is the derivative of that integral? The answer is x over 1 plus x squared. Because my upper bound is x and only x. Okay? The derivative of this integral is exactly that, but instead of t's, we threw in the x. Okay? That's what we just proved up above. Okay? That's what we did in Belwork as well. It's a thing. Okay? If you don't believe me, take the antiderivative and work it through. Okay? But derivatives and integrals are opposites of each other. And so when I do one and then the other, it makes sense that I just come back with what I started with. Good question. Everybody good with that? When it's an x, they're super easy. If it's a little bit more complicated, we got to do a little bit of work. So let's look at number 2. Okay? Number 2 says, find the derivative if y equals 1 to the x squared. Okay? So again, x needs to be in the upper bound. If it's not in the upper bound, we got to flip our integral and we got to make it negative. Okay? We're good here though. X squared is in my upper bound. It's cosine of t dt. So again, let's break it into two parts. The first thing we're going to do is find the integral of this thing. Let's find the integral of that thing. And so I'm going to start off by finding capital F of t. What is the antiderivative of cosine? What comes before cosine? Sine comes before cosine on our wheel. And so sine of t, that's my antiderivative. I'm going to evaluate that thing starting at 1 and going to x squared. So to evaluate that thing, I'm finding capital F of x squared minus minus capital F of 1. I found the antiderivative. I'm going to plug in upper bound minus lower bound. Now we're going to do it. So let's plug it in. X squared. So it's going to be sine of x squared minus sine of 1. That is the definite integral. Starting at 1 and going to x squared, this is what you get. If that's all the problem said, I would be done, but that's not all the problem said. The problem said, cool, we're finding that, but it also asked us to find the derivative of that. By saying this guy right here, it's saying find the derivative. So I'm going to take this thing and I'm going to find the derivative of it. Sorry, dx. Find the derivative of that. What is the derivative of that? Work with your neighbor. Find the derivative. We're finding the derivative of this thing. Sine of x squared. We're taking the derivative. What special rule are we using here to take the derivative of sine of x squared? This is a chain rule. You got a mama and a baby in there. Okay? The outside function is sine. What's the derivative of sine? Cosine. We took the derivative of sine to get me cosine. I rewrote the baby. But then don't forget, we got to multiply by the derivative of the baby. The derivative of x squared is 2x. That's the derivative of this first chunk. What's the derivative of minus sine of 1 going to get me? Nothing. There are no variables in that. That is just a number. Sine of 1 is some number that I don't know. Okay? I don't care what it is anyways. It's 0. And so my final answer here is 2x cosine of x squared. That is the derivative of my initial integral. It wasn't as easy as the first problem. Okay, the first problem, whatever it was said, that's what it was. Here, cosine became 2x cosine x squared. Let's show you the shortcut of how we did this. Again, we did this in bell work. Let's see how we do it here. We took my upper bound. We made sure x was in our upper bound. We plugged it in. Okay, that's where this cosine of x squared came from. Where did that 2x come from? It's the derivative of my upper bound. The derivative of x squared is 2x. So if we look at this next guy, number 4, okay, it's a derivative of this integral. It starts with a number, it goes to x. So x is in my upper bound like I wanted. So if I want to take the derivative of this integral, we take the upper bound, we plug it into my problem. So it's going to be e to the 4 times 3x squared minus 6. I plugged in my upper bound. What else do I need to do with this thing? Multiply that by the derivative of what I plugged in. Since I plugged in 3x squared, I'm going to multiply by 6x. And so my answer is 6x e to the 12x squared minus 6. I just multiplied 4 times 3. Questions on how we did those? Try example 5 and 6 on your own. On example 5, x is in my upper bound, a number's in my lower bound, so I'm good with this. I can plug in 2x for both t's in this problem. So it became 2x to the 5th minus 9, 2x to the 3rd. That is not it, though. What else do I need to do with that thing? All of it by 2. It's got to be in parentheses. If you didn't throw parentheses in there, you didn't multiply the whole thing by 2. It's all got to be multiplied by 2 because the derivative of my x is 2. Once I've done that, I can evaluate it. 2x to the 5th, that's 32x to the 5th because I'm taking it to the 5th power. 2 to the 5th, x to the 5th. Minus 2 cubed is 8, times 7 is 72. I'm sorry, times 9 is 72. X cubed. I still haven't taken that times the 2 yet. My final answer, simplified, is 64x to the 5th minus 144x cubed. You might not have simplified. If you left it just like that, you're good. Okay, the simplified answer's on bottom. Question?
Yeah, can we go over why it's multiplied by 2 again?
Yep, because it's not just x up here. Okay, because it is something beyond x. The derivative of x is 1, and so we don't have to multiply by the derivative of the exponent, or the derivative of my upper bound. But I have to multiply by the derivative of my upper bound. The derivative of 2x is 2, and so I multiply everything that by 2. Again, that's what we did in this first problem. Okay, when we plugged in that x squared, it gave us that cosine x squared like we wanted, but the answer we found when we did it the long way was 2x cosine x squared. Where's this 2x coming from? That 2x is coming from the derivative of my upper bound. Okay, the derivative of my upper bound here was the derivative of 3x squared was 6x. The derivative of 2x here is 2. That's what I'm multiplying by, because it's not just x in my upper bound. So as I set up this guy, I'm plugging in x to the 4th. So it's x to the 4th square rooted times the derivative of my upper bound. So the derivative of my upper bound here is going to be 4x cubed. If we wanted to simplify, what is x to the 4th square rooted? That is x squared. And know why. We didn't take the square root of 4. Okay? What would this be? What would the square root of x to the 9th be? The answer is to the 9/2, right? Because what does square root mean? It means you are raising something to the 1/2 power. How do you deal with power on powers? You multiply them, okay? And so be careful with that. That's something you might have forgotten. But this is times 4x cubed. My answer is 4x to the 5th. Questions with that one? Flip it over. Here we go. So we are evaluating this thing. They say capital F of x is equal to this integral. We are finding capital F of 0, f prime at 0, and f prime at 3. So let's start off with our first one. The first thing it asks us to do is to find f of 0. They told me right here that capital F is this thing, is that the integral of 2t squared minus 2. So if I want to find capital F of 0, what do you think I'm going to do? Plug 0 in for x. I'm plugging in for x. That's an x value. Okay? These are x values because it's capital F of x. And so to find capital F of 0, I'm going to plug in a 0 right there because it's that integral. We're starting at 0. We're going to go to 0 of 2t squared minus 2 dt. Guess what happens when you find the area under the curve starting at 0 and going till 0? It's 0. The answer to that question is 0. What is capital F of 0? It's 0. If it were a number there instead of 0, if it had been like 6, then you take the antiderivative, you evaluate that thing from 0 to 6, and you're good. But that one's pretty straightforward. Let's do the next one. So now we're finding f prime at 0. F prime at 0. Or in other words, I am taking the derivative of this integral. That's what it asks you to do. Find the derivative of this guy. How do I find the derivative of an integral? That's what we just did on the front page. How did we find the derivative of this thing? We plug in. There's nothing fancy here, right? The upper bound is x. This is easy. All I have to do is plug it in. What is capital F prime of x? F prime of x, without evaluating it, is just 2x squared minus 2. The derivative of the integral is just what you started with. Because the upper bound is just x, the derivative of the integral is that function. They cancel each other out. So it's just 2x squared minus 2. That's what f prime is. I'm trying to find f prime at 0. Show me with your fingers. What is f prime at 0 going to be? Negative 2. You take that 0, you plug it in. Your answer is going to be negative 2. Find f prime at 3. Again, nothing different here. We take 3, we plug it into that equation. The answer is 16. Once you figure out what the equation is, you could evaluate those things all day long. Okay, just a matter of understanding what's happening with those. Questions with those two? The next question is the exact same thing. They tell you what G is. Capital G is equal to this integral. So they're asking you to find capital G of 0. That thing is super easy. To find capital G of 0, they told me what the G equation was. I'm going to evaluate that thing starting at 0 and going to 0 squared of square root of t cubed plus 3. What is the area under the curve starting at 0 and going to 0? 0. That's the first one. The second one, though, is asking for G prime. You're asking for G prime at 1. Or in other words, you've got to take the derivative of this integral. Take a second with your neighbor and figure out what is G prime at 1 going to leave you with. We are finding the derivative of this integral. So let's start off by figuring out what G prime of x is. What is the derivative of this integral? Okay, I'm taking the derivative of an integral. Is x in my upper bound? Yeah, it is. But the problem is it's x squared. So we're taking this x squared, we're plugging that guy in, and so my problem is going to look like this. The square root of x squared cubed plus 3. What else do I need to do with this answer then? Or with that function? Multiply by the derivative of what I plugged in. Since I plugged in x squared, I'm multiplying it by 2x. So when I want to find capital G prime at 1, it is the square root of 1 to the 6th plus 3 times 2. 1 plus 3 is 4. Square root of 4 is 2 times 2. My answer to this question is 4. It's applying what we learned on the front side to a more AP style question. Everybody good there? All of that stuff, everything we have done to this point is getting us ready for this question right here. Okay? This is the big one. Out of everything else we've done today, this is what I care about the most. The graph of y equals f of x is shown. Okay? For some reason, Microsoft Word hates me. Where this is supposed to say capital A of x. It's like the most important thing on this whole worksheet, and it didn't print right. Capital A of x. Let capital A of x be equal to this integral. Okay, our job is to find a of 2, a of 3, a prime of 2, and a prime of 3. These are the last 4 things we'll do today. Okay, so let's start off by finding capital A of 2. The first thing I would always tell you to do is to label that graph. They're asking for A, but that graph is of F, and that blows my mind. That's not what I want at all. I want A. They have F. A is equal to the integral of F. What could I label that graph as? This is an A prime graph. It is the integral of F. Okay? Capital A stands above F. It's above it because it's the integral. So if we're going down to F, that is the derivative of A. Okay? It is an A prime graph. Okay? Think of it this way. A is the integral. We start off with F. If we take the antiderivative, if we take the integral, we go up to A. So if I'm going back down, it gives me F, or in other words, A prime. It's the derivative of that guy. So I want to find capital A of 2. Well, this one's pretty easy. Okay, capital A of 2. Oh, here's my equation to find capital A. It's equal to, starting at 0, going to 2, of f of t dt. What does that mean I'm doing if I'm starting at 0 and going to 2 and I'm finding the integral? Area under the curve. I want to find the area under the curve starting at 0 and going to 2. What is this area under the curve going to get me? That's going to get me 4. Okay, it's just finding this box. This box right here is 4. That problem is done. Great, now let's do the second one. The second one says find capital A of 3. Take a second with your neighbor and do that. The question didn't change much. We're still finding the area under the curve. The only difference is this time instead of stopping at 2, we're going all the way to 3. And so it's still 4. I got another box of 2 right there. So this is 6. And then we got this 1/2 guy right there. The answer, what is capital A of 3? It's 6.5. 6.5, 6 1/2, however you want to write it. Those are pretty easy. The next one's even easier if you know what you're looking for. The next question says, let's find A prime at 2. What is that graph a graph of? This is a graph of A prime. The question is not, careful with this question. This is a graph of A prime. If I want to know, looking at A prime, what is A prime of 2? Show me with your fingers. What is A prime at 2 going to get you? It is 2. Because it is a graph of A prime, all you need to do is go to 2 and look at the y value. The answer is 2. That is a different question, and I don't even want to get into this because I don't want to confuse us. A double prime. What would A double prime be? Undefined, because you would be looking for the slope right here. I can't tell you the slope right there because it's a corner point. Because A prime, A double prime would be the slope, but that's not what we did here. So the last one, look at it. A prime at 3. Show me with your fingers, what is A prime at 3 going to be? A prime at 3 is 3. Problem solved. Okay, this is where we're headed. Tomorrow we're going to do a whole lot more graphs. Remember back to first semester when we said like F is concave up, means F prime is increasing, means F double prime is positive? That's a really important chart for us to remember. Where do maximums and minimums happen? That's where we're going tomorrow. Okay?